less than 8.2. You guys are so close to the end. I'm so happy. But then my real work begins. All right. We are finding the area between two curves today, which is not that hard, but there are some tricky aspects to it. We know that the integral from a to b of f of x dx produces signed area, which may be positive, negative, or zero. We know that if it's above the axis, that area is positive. If it's below, it'll be negative. However, if we're asked to find the actual area, that cannot be negative because area must be positive, because in real life, there would be no negative area. That's kind of a weird thing. So we want to find the area between two curves. Then all we have to do is subtract. Really, we could find the area of the top curve. We could find the area between the x-axis and the bottom curve, and if we subtract, we're going to get the area between. And so we just simply do essentially top curve minus bottom curve, which is pretty easy to do. It is important that f of x and g of x are continuous, but also make sure that your function f is greater than g. Otherwise, things will get kind of weird. So you always literally have to make sure something's on top the whole way. Or, as you'll see later, we're going to split up the area. Okay, we're going to split up the region. So normally our functions are in terms of x, but there are times when our functions are going to be in terms of y. Excuse me. In which case, if we want to find the area between the curves, we want to do the right side curve minus the left curve, which you'll see we're going to do an example. Okay, so let's just try one here. We want to do example number 1. We have this lovely curve here, and it is important that you sort of visualize what's happening. So especially on an AP test or something, you might want to draw a little picture, draw a little sketch, okay? Lots of drawing here. X squared plus 2, we know, is a parabola shifted up 2 units. So you can see here we have this portion of a parabola. We have the line y equals x. This was the green line. I guess I'll put my y equals. Okay. And then we have this boundary line x equals 0. That's our vertical line here. And this boundary line x equals 1. So we want to find the area between, inside that region. And we can see that it's bounded on the left and the right by x equals 0 and 1. That's going to give us our limits of integration. And we want to do top curve minus bottom curve. So I'm just going to I'm going to go ahead and use brackets. So I'm going to do x squared plus 2 minus the green bottom curve minus x. And I'm putting this in parentheses like this just so you can, since we are subtracting, you do have to be very careful. Subtracting g of x is very, just y equals x is very easy to do. But if that was a more complicated function, you have to be careful of that negative and make sure you're subtracting everything. Thus, the parentheses. If you use parentheses, you'll always get it right. I can clean that up, and that's going to be the integral from 0 to 1. Let's see, x squared minus x plus 2 dx. And then we're going to go ahead and integrate. What is the antiderivative of x squared? X cubed over 3. And the antiderivative of x squared over 2 with a negative in front. And the antiderivative of 2 is 2x. And again, we're integrating from 0 to 1. I can go ahead and plug in the 1 there. And we would have 1 cubed over 3, which is 1/3. 1 squared over 2 is 1/2 plus 2. I guess I'll make those all with a denominator of 6 so I can add them easily. So that's going to be minus 3/6 plus 12/6. Oh, I forgot to subtract all the zeros. That's a 0, 0, and 0. So, yeah. Sorry about that. I forgot the zeros, but it is just minus 0. I'll squeeze that in here. Minus 0 for all the others. All right. 2/6 minus 3/6 is negative 1/6 plus 12/6 is 11/6. All right. So not too hard. Of course, this was a nice straightforward problem just for practice, just to see what we've got. But sometimes we have to find where two curves intersect to determine the boundaries. This one, it was really clear. We were going from 0 to 1. But we do sometimes need to find the boundaries for your regions. What is our integration? What are the limits of that integration? These intersections will provide you the limits of your integration, and you must show an equation setup, even when using a calculator, to find those intersections. This first one we're going to do by hand, but number 3, we're going to use a calculator. And so example 2 is an example of functions in y, okay? We're very much used to functions of x, where we have our equation for y in terms of x. But here, you can see we've got two different things going on. We have x equals y squared minus 3. That looks a little bit funky. We don't normally see that. Y equals x plus 1. Well, that's pretty standard. We know what that looks like. I'm going to go ahead and draw that. Y equals x plus 1, y-intercept of 1, and we go up 1 and over 1. So I'm going to go back and sort of make a little sketch here, as close as I can. There we go. So there is my line. All right. I'm not going to label it yet. Now, what is this thing? X equals y squared minus 3. A sideways parabola, yeah. If you think about, normally we would see y equals x squared. Well, that one would be, oh God, I can't do this way. A parabola this way, being x squared minus 3, but since the y is being squared, it's been flipped on its side. So now it's going sideways. Now, maybe you don't know that, and that makes that rather challenging. So you could always plug in y values to get like a sort of like an XY chart, essentially, into your equation if you weren't sure. Let's see. So what I'm going to do is, let's see, they've got y squared minus 3 has a, if y is 0, the x is negative 3. Let's see, if, what happens when x is negative 2, I would have to add 3, so I would get 1 equals y squared. And when we take a square root of that, we get plus or minus 1. So when x is negative 2, we get a plus or a minus 1 right there. All right, so sort of like that, that's what I'm doing. What if x is 0? No, let's see, what if x is 1? So if x is 1, I'd have y squared minus 3. So again, I'm going to add 3, and that would give me 4 equals y squared. When I take a square root, that would give me y equals plus or minus 2. So when x is 1, I'm getting y equals 2 and y equals negative 2. So didn't really know what that function looked like, but here it is. I found some nice x values and then solved for y. So here is my curve. And again, that's not really something, you know, you can graph in your calculator, but more than that, what if you didn't if you're not able to use your calculator, which is incredibly likely on a problem like this. So again, you can always just pick X values, pick Y values, and plot those as much as you can. So now you'll notice here, we have this sort of weird area between the curves, this sort of region in the middle here, all right? And you'll notice over here between -3 and -2, if I were to subtract that curve, I'm subtracting from itself. So I can't really do that, all right? Because of that, I have to do left and right. Got my left side curve here, or sorry, right side curve, and this is the left side right here. What we're going to do is we are going to integrate horizontally. We're going to go this direction. So we're taking horizontal slices, or subtracting horizontal Y values. And so then we're always going to be subtracting the right side minus the left side. And all the way along, we can do right minus left, right minus left. And so that's sort of an interesting thing to see there. We are going to integrate with respect to Y horizontally, which means I need everything in terms of Y. We can see that Y squared minus 3, that already has Y's in it. This curve, I need to rearrange a little bit. I'm going to have Y minus 1 equals X. So there is my curve in terms of Y. I'm going to write that down over here. This blue curve is X equals Y minus 1. And my pink curve was right there. X equals Y squared minus 3. A little bit of rearranging there. Now, I happened to find my intersection points here. But if I needed to find them, we could substitute. So just as an aside note here, we have our equations, X equals Y squared minus 3, and we have X equals Y minus 1. We can do a little bit of substituting, set them equal to each other. Y squared minus 3 equals Y minus 1. And I'm going to set everything equal to 0. Y squared minus Y. When I add 1, I'm going to get minus 2 equals 0. And we can double bubble. So we get Y times Y is Y squared. And let's see, -2 times +1 would give me -2. And that's fine. So I get Y values of 2 and -1. That helps me with my limits of integration here, because this ordered pair was -2, -1. And this ordered pair, whoop, right there, was 1, 2. And because we're integrating in terms of Y, we want to take those Y values. That's going to give me my low Y value and my high Y value that we're integrating from. All right. Okay. So how do I set this up? Here we go. So you could always, once you had these Y values, if you wanted, again, your picture, you'd plug them back in, like right there, just to get the corresponding X value. Okay. But we don't need those. All right. So I'm going to integrate to find the area of the region. So we're integrating from my low Y value of -1 to my high Y value of 2. So -1 to 2. And we want to do the right curve, the blue curve, minus the green curve. So that would be, again, I'm going to use parentheses, my Y minus 1 minus the green curve, again with parentheses, which is Y squared minus 3. And we are integrating this in terms of Y. So everything has Y's in it. We're using Y ordered pairs, the Y coordinate rather, and lots of Y's. And here is this most tricky part where everybody makes the mistake, the distributing of the negative, thus the parentheses. Have to be very, very careful. -1 to 2. I'm going to clean this up a little bit. I have a y. This is going to be a -1 plus 3. Negative times -3 gives me a +3. So that's going to be +2. And then negative times y squared is negative y squared.
Not working. I have a brand new one. If it's not working, go away.
So just cleaning that up just a little bit to get rid of the crazy negatives. Now I can integrate. Oops, daisy, I didn't need that. Sorry. Since I'm at the integration stage, I don't need my integral anymore. All right, y becomes y squared over 2. 2 is going to turn into 2y. And negative y squared is going to be negative y cubed over 3. And we are integrating or plugging in -1 to 2. All right, plugging in my 2. 2 squared over 2 would be 4 over 2, which is 2. 2 times 2 would be 4. And then 2 cubed is 8 over 3 is 8/3. So there's my substitution of 2. And then we're going to subtract. Now we're going to substitute in the -1. -1 squared is what? 1, +1. Be careful. 1/2. All right, then we have 2 times -1. That's going to give me -2. And then we have minus a -1 quantity cubed. What does that turn into? +1. Yeah, good. -1 cubed is -1 times the negative would give us +1/3. Let's see. I'm going to put all the whole numbers together, I think. Let's see. So 2 plus 4 is 6 minus a -2 becomes 8. So that was that one, and that one. And let's see. Oh, I can add the -8/3 and the 1/3. So -8/3 minus 1/3 would be -9/3, which is -3. And then I have a -1/2. All right, 8 minus 3 is 5, minus a half, it was 4.5. Ha! Well, that was easy. Okay. That's some tricky math there. It's a good review. That's why we practice that. Again, though, on an AP test, you could totally leave it right there where everything is plugged in and subtracted like that. Totally nice. All right. Any questions on that one? This is something we want to be pretty careful about, that we are subtracting horizontally, the right side minus the left side. So because those are little...
Excuse me, Marsha, is this time with any high school boys interested in playing golf and any high school girls interested in playing tennis? Please report to the gym for a short meeting. Thank you.
All right. All right, let's see. All right. We're going to be doing more with these horizontal, subtracting right from left horizontally like this. So, all right, here we go. Example 3, set up the integral for the total area of the regions located between the two curves as shown. We may use a calculator. So first I want to figure out which curve is which here. And let's see, f of x is x cubed minus x squared, and then g of x is negative x squared plus 4x.1, or 4.1x rather. I think I'm going to do, because I'm more familiar with x squareds, this is my g curve, is a parabola, and so I know that that would be this parabola shape. All right, so I'm highlighting that just so I can see it really clearly. There's that parabola shape, which means the cubic must be the other one. So I'm going to do that. And you'll notice here on this curve, when we think about finding the total area between the curves, we have to do top minus bottom. Well, top minus bottom, that'd be green minus blue. But over here, top minus bottom is blue minus green. All right, so they change. And so we have to be aware of that. And that's the biggest thing, I think, when we're finding the area of the region between two curves. We have to make sure that, you know, if we're doing green minus blue, we're integrating over that region where green is on top. So in this particular case, we have to break up this integral into two integrals. One where the green is on top, and then another integral for where the blue is on top, okay? And so that's something we want to pay attention to. Now we want to find all those intersection points. I do know one intersection point right here is 0, 0. I can see that pretty easily from the graph, but also if I plug in 0 for x, I'm getting a 0 and I'm getting a 0. But we're going to graph these to see how we use our calculator. So we're going to type in both of these functions, x cubed minus x squared, and then negative x squared plus 4.1x. Oh, and I'm in degree mode. You guys need to double check. If we're using my calculators, doesn't need to be in radians for this, but I just, okay. There we go. Let's see. This window that we're showing here goes from -2 to 3, so I'm going to go ahead and change my window just so my picture looks pretty similar. My y values go from -12, I'm going to make it -13 to 5. So I'm going to change my window just a little bit and graph. Okay, and so we can see pretty clearly some intersection points here. We need to find those points of intersection so that we can figure out what our integration boundaries should be. I'm guessing it's -2, but I'm going to go ahead and calculate the intersection. I'm going to move Tinkerbell to the quick curve, the one that's less curvy. All right, and do enter, enter, enter. And so we can see this, whoops, no sign change. I didn't go far enough. Let me change my window. Let me go -3. There we go. Now they're crossing a little better. Let me try that one more time here. That's good. No sign change means your window's just not in the right spot. All right, red curve, okay. So here's some interesting tips for you because this is really important. This intersection is -2.024846, -12.4018. So these are rounded off, and you do not want to round them to 3 decimal places. You absolutely need to store these. The nice thing is your calculator automatically stores these values for you in X and Y. All right, so what we're going to do is just to show you, I'm going to quit, and if I just type in X, there's that X value right there. So I was here in the graph and it had showed me my X and Y value for the intersection. The calculator automatically stores those values as X and Y. So I went ahead and did a second quit, and then I said X and just hit enter. So you can see that it's storing that X value there. Okay, but what I want to do is I am doing top minus bottom. So I'm doing vertical subtraction here, top minus bottom. So I'm using X values then. I want to restore that X value. I'm going to use P. I'm going to let P equals -2.024844, yada, yada, yada. So what I'm going to do is I'm going to go ahead and store that. And so that's, I just hit store, and it's going to take that answer. I'm going to do alpha P, just to store it in P for now. So you hit stow, you stow it, okay? So I wrote that down. A reader, AP reader would read that and recognize that I'm using P to represent that value. Now, the reason I did that is because when I go to graph and find the other intersection, it's going to store over that previous X value. And so I'm going to go again and calculate the intersection. So I'm going to move Tinkerbell again to my other intersection, enter, 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 and so I get this intersection at 2.0248 yada 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 and 4.20186. Again, I'm going to store this X value. So I'm going to quit. Again, you can see now when I call up X, there's that positive 2.02 value. Also, if I did alpha Y, so I did alpha Y, and there's the Y value. So it stores both of those in X and Y. Now I need to rename it, so otherwise I'm going to lose it. So I'm going to make that a Q. Q equals 2.0248 yada yada yada. I'm going to store that, so I'm going to hit store, and I'm going to do alpha Q. So I'm storing that 2.02 value in Q. Now, the nice thing is I don't have to write out those big crazy decimals. I don't have to round anything off because it's saved in the calculator for me. And now we're going to integrate. So I'm going to do, to find the area between the curves, first we're doing this section where green's on top. And so I want to integrate from P, that -2 value, so P, all the way to 0. And I'm going to do the green curve, which I'm just going to call f of x. Green curve, top curve, minus the bottom curve, minus the blue curve. So I'm going to subtract g of x, dx. This is exactly how I'd write it on the AP test. I'm going to make it as simple as possible, no mistakes. I don't have to use the whole minus x squared plus 4.1x. You can, but use parentheses, otherwise they're going to get marked off, okay? And then, now I'm going to do my second integral where blue is on top. So now we're integrating from 0 to our intersection, which is happening here at point Q. I guess this is like point P right here. So from 0 to Q, and now we're doing top minus bottom. Top is going to be blue. My blue is the g of x curve minus the bottom f of x curve. Okay, this is the setup. This is something you'd write down on your free response AP question. That's all you need. It's so elegant. It's so precise and convenient. And what we're going to do then is I'm going to use our calculator to solve these. We put f in y1. I'm going to make a little note of that. That's y1. And we put g in y2. So that's my y2. And so now I'm just going to make sure that I do those. I'm going to quit. I'm going to do math 9. And we are integrating from p. So I can actually do alpha p to 0. We're doing f of x minus g of x. That would be y1 minus y2. So I'm going to do y1 minus y2. Plus another integral, math 9. Now we're integrating from 0 to q, so alpha q. And now we're doing g minus f, so that's y2 minus y1. So y2 minus y1 in terms of x. All right? So lovely calculators here. It just makes life so nice and easy and, you know, brilliant. So we get $8.405 for that and yeah, there's a lot of calculator work we're doing. Which is, you have to do them separately, right? Because when we do top minus bottom on between in this section, it would be green minus blue. But when we switch here to do top minus bottom, now it's blue minus green. That's why I color code things, just so we can really see, hey, we have to break this up. Otherwise, the area is going to get all discombobulated because this would be a negative area there. So we have to be a little careful. But everything is in the calculator. All right, you got questions for me?
So you just found intersection points on the calculator?
Yes.
So, okay.
And